This mini-lecture introduces Lewis structures, a method for determining the molecular structure of covalent compounds. When combining Lewis symbols to create Lewis structures for molecules, there are some rules to follow. First, electrons that appear in the space between two atoms count towards the octets or duets for both atoms and represent a shared pair of electrons, referred to as a bonding pair. Each bonding pair counts as one covalent bond, and it is possible to have more than one pair of electrons shared between the two atoms. Any pairs of electrons that are not between the two atoms are referred to as lone pairs and will not be involved in the formation of a bond. So they do not count towards the number of bonds in the molecule, but they do count towards the octet rule for each atom that they are adjacent to. Looking at the example for water, H2O, note that the bonding pair between the oxygen and hydrogen satisfies the duet rule for the hydrogen. And if we count all the electron dots surrounding the oxygen, we see that there are a total of 8 electrons, satisfying the octet rule for oxygen. So in this case, 4 of those electrons exist as bonding pairs, and 4 of those electrons exist as lone pairs on oxygen. Below are some Lewis structures of diatomic elements, those nonmetal elements that exist as diatomic molecules in their natural state. For chlorine, Cl2, just one electron from each atom is shared in order to attain a complete octet on both atoms via a bonding pair. The same is true for hydrogen, H2, except here the duet rule is being satisfied. For oxygen, O2, each oxygen shares 2 electrons in order to attain a complete octet on both atoms via 2 bonding pairs, leading to a double bond for oxygen. And something similar happens with nitrogen, N2, where 3 electrons are shared between both atoms, leading to 3 bonding pairs and therefore a triple bond for nitrogen. Now, it's often simpler to draw the bonding pairs simply as bond lines, where we use one line to indicate one bond and multiple lines to indicate multiple bonds between the two atoms. So from here forward, be mindful that a single bond line counts as 2 electron dots in a Lewis structure. So if you have more than one line, you have more than 2 electrons involved in bonding. For more complicated molecules, a very specific set of steps is used to accurately predict the correct structure. And I'm going to walk through these steps 3 times with the 3 molecules below. Now, it doesn't matter which of the first 2 steps you decide to do first, but I'll start with the hardest step of predicting the correct skeletal structure for the molecule, which is just the general arrangement of the atoms. This involves choosing a central atom, or multiple central atoms if you have a very large structure. To make this prediction, first consider that hydrogen atoms only need 2 electrons to satisfy their duet rule, so they can only form one bond with another atom. Therefore, hydrogen is not suitable as a central atom because central atoms usually involve forming multiple bonds. So we expect hydrogen atoms to be terminal, meaning they bond to a central atom and lie on the outer edges of the structure. Central atoms need to be able to share multiple electrons to complete their octet, and they do this by forming multiple bonds, sometimes to multiple atoms. Central atoms are often listed first in the molecular formula for the molecule, as we see with all 3 examples below. Nitrogen and carbon will often act as central atoms because nitrogen needs to share 3 electrons to attain a complete octet, and carbon needs to share 4 electrons. However, listing the central atom first in a molecular formula is not a hard and fast rule, and it also doesn't work well when there's multiple central atoms in a structure. So a better way of determining the central atom is to consider electronegativity. Elements that are least electronegative will usually be central atoms, and elements with higher electronegativity will usually be terminal. Electronegativity becomes even more important when dealing with complicated Lewis structures, but since the structures we'll be discussing below are fairly straightforward and simple, we'll just note this rule for now, and we'll wait to discuss electronegativity in more detail in the next mini-lecture. So, let's begin with NH3, also known as ammonia. Based on all the rules, we can predict that the skeletal structure for ammonia places the nitrogen as the central atom, since hydrogen cannot be a central atom. Therefore, all the hydrogens will then be attached to the nitrogen, and I've arranged them on 3 out of the 4 sides of the atomic symbol for nitrogen. The next step is to determine the total number of valence electrons that will need to be represented by electron dots in the structure. This can be done before or after determining your skeletal structure. We count the valence electrons by noting the column in the periodic table where the atom is located. Hydrogen is in the first column of the periodic table, so each hydrogen contains 1 valence electron in the 1s orbital, for a total of 3 electrons from the 3 hydrogens in this molecule. Nitrogen is in the 5th main group column, group 5a, indicating that it has 5 valence electrons, so 2 in the 2s orbital and 3 in the 2p orbitals. Altogether, this makes for 8 valence electrons for ammonia, so we need to place 8 electron dots onto our structure for ammonia. Now, for polyatomic ions, you will need to add or remove electrons based on the overall charge on the ion, but we'll save an example of that for later. Next, we distribute the electron dots, starting first with placing a bonding pair between each set of atoms where a bond is implied. When we formed our skeletal structure, we were laying the framework for bonding in the molecule, as each pair of adjacent atoms needs to be connected to each other through at least one bond. And we'll start by assuming that all of these bonds are single bonds between the atoms. We then subtract the number of electrons needed to form those single bonds from our total valence electrons to see how many remain. So 8 minus 6 gives 2 remaining electrons that need to be placed on the structure as a lone pair. And we look first at the terminal atoms to see if they need any more electrons to satisfy the octet or duet rule. All the hydrogens in this structure are satisfied, so we move to the central atom and note that nitrogen is actually missing 2 electrons to complete its octet, so the lone pair must be placed on the nitrogen. Finally, we double check the structure. Have we accounted for all 8 valence electrons on ammonia? No more, no less? Does each atom in the structure satisfy the octet or duet rule? In this case, we can say yes to both questions, so our structure is complete. If you prefer to show your bonding pairs as bonding lines, as I do, then you would represent your structure as shown below. Just remember to count each bonding line as 2 electrons when double checking the total valence electrons and the octet or duet rule. On the next 2 structures, take a moment to pause the lecture and see if you can determine their Lewis structures on your own. Ready to review? The skeletal structure for CF4 predicts carbon as the central atom, as fluorine only needs to share 1 electron to complete its octet, but carbon needs to share 4 electrons, so it requires more bonds. So each fluorine is attached to the central carbon. Next, we count valence electrons. Fluorine is in the 7th main group column, group 7a, so each fluorine contains 7 valence electrons, for a total of 28 electrons from just the 4 fluorines in this molecule. Carbon in the 4th main group column, group 4a, adds another 4 electrons, so we get a grand total of 32 valence electrons that need to be expressed as dots in the structure. Next, we distribute the electron dots by placing a bonding pair between each set of atoms where a bond is implied. And we subtract the number of electrons needed to form those single bonds from our total valence electrons. So 32 minus 8 gives 24 electrons that need to be placed on the structure as lone pairs. And again, we look first at the terminal atoms to see if they need any more electrons to satisfy the octet or duet rule. Each fluorine needs 6 more electrons to satisfy the octet rule. So we add 3 lone pairs to each of the 4 fluorines. This accounts for all 24 of the remaining valence electrons. Note that carbon's octet rule is already satisfied by the 4 bonding pairs surrounding it. Finally, we double check the structure. Have we accounted for all 32 valence electrons on CF4? No more, no less? Does each atom in the structure satisfy the octet rule? Again, we can say yes to both questions, so our structure is complete. And again, this is what the structure would look like with bonding lines used for the bonding pairs instead of dots, and you'll notice in this case, This is particularly useful because it cleans up the structure a bit and makes it a lot easier to see which of the dots are actually bonding pairs. On to CO2. The skeletal structure for CO2 again predicts carbon as the central atom, as oxygen only needs to share 2 electrons to complete its octet, but carbon needs to share 4 electrons, so it requires more bonds. So each oxygen is attached to the carbon atom. Next, we count valence electrons. Oxygen is in the 6th main group column, group 6A, so each oxygen contains 6 valence electrons, for a total of 12 electrons from the 2 oxygens in this molecule. And since carbon adds another 4 electrons, we get a grand total of 16 valence electrons. Next, we distribute the electron dots by placing a bonding pair between each set of atoms where a bond is implied. And we subtract the number of electrons needed to form those single bonds from our total valence electrons, so 16 minus 4 gives 12 valence electrons that need to be placed on the structure as lone pairs. Each oxygen needs 6 more electrons to satisfy the octet rule, so we add 3 lone pairs to each oxygen. This accounts for all 12 of the remaining electrons, so since we're out of electrons, we can't add any more to the structure and we stop here. But finally, we need to double check the structure. Have we accounted for all 16 valence electrons on CO2? No more, no less? Yes, we have. But does each atom in the structure satisfy the octet rule? No, not in this case. Right now, carbon only has 4 electrons around it, and it actually needs another 4 electrons to satisfy the octet rule. But since we can't add any more electrons to the structure because we've already used up all our valence electrons, then we must reconsider the bonding between the carbon and the oxygens. This must mean that carbon has more bonding pairs than the 2 that we've already indicated. So we take lone pairs from the terminal oxygen atoms and make them into bonding pairs to satisfy the octet rule for carbon without changing the number of electrons around the oxygens. So note here, oxygen still has 8 electrons around it, and now carbon has 6. If we do this for each oxygen, we now see that both the oxygens and the carbon obey the octet rule in this new structure, where there are now 2 bonding pairs, or 2 bonds, between each carbon-oxygen pair. Finally, this is what the structure would look like with bonding lines used instead of the dots for the bonding pairs. And we can clearly see that there is a double bond between each carbon-oxygen pair. For polyatomic ions that have an overall charge, we add up the valence electrons for each atom as we normally do, but add an electron for each negative charge or subtract an electron for each positive charge. So in the case of NH4+, also known as the ammonium ion, the positive charge means we subtract an electron from the total valence electrons of 9 to get a final total of 8 valence electrons. We then build up our molecule in the same way, starting with the skeletal structure, adding bonding pairs between the atoms, checking to see if any remaining electrons need to be added as lone pairs, and checking that all atoms obey the octet rule. The one final difference for ion structures is that we surround this entire structure with square brackets and indicate the overall charge in the upper right corner outside the brackets. This explains to someone viewing the structure why there are only 8 valence electrons indicated in the structure when you would typically expect a total of 9 since there's 1 nitrogen and 4 hydrogens. This concludes the second mini lecture for Chapter 6. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza, and I will also take questions on this material during one of our virtual class meetings, and during that time we will focus more on problem solving for concepts in this chapter.